morning, you wonderful physics kids. We're going to do Enigma number 8 today, and this is talking all about the coefficient of friction, how we figure out the coefficient of friction, and ideas about that. Now, in order to start that, the first thing we really need to do is to talk about a free body diagram. All right, so let's talk about a free body diagram. You'll see in the box on the top, we start talking about net force. Why do we talk about net force and free body diagram when we're talking about coefficient of friction? Take a look. On a free body diagram, we're going to attach all the forces acting on an object. One of the first things we have to understand is if there is a net force, there is an acceleration. If there's a net force, there's an acceleration. There is never a time when that is not happening. So if there's no acceleration, what can you say about the forces acting on an object? All right? If there's no acceleration, the forces acting on an object must be in balance. So an object moving at constant velocity, let's think about that. If we have an applied force here, what's the force of friction? Force of friction must be equal and opposite, exactly equal and opposite. If we have a weight pulling it down, well, what's the force pushing up? That's the normal force. How do they compare? Well, if there's no acceleration, they must be equal and opposite. So all the forces in this situation are balanced. Key. If one of the forces was a little bit larger, then you would have a net force, and you would have an acceleration. So why do we have to talk about this now? Take a look at this. The formula for the coefficient of friction is force of friction equals mu times the normal force. So when we solve that, for mu, we have F sub F over F sub N. Great. How do we determine F sub F? In other words, when you're dragging something, how do you know what the frictional force is? You don't really have a scale that would measure the frictional force. All right? So when you're dragging something, if you put a scale on the side that you're dragging it on, and you find it's 15 newtons worth of force, and that's the force applied, and that object is not accelerating. Can you tell me what the force of friction on that object is? Well, has to be 15 newtons. Do you see? Because the forces are in balance. It's not accelerating, so the force of friction must be equal to your applied force. Similarly, you can measure an object's weight, put it on a scale, that's easy, but can you measure how hard the floor is pushing up on it? But that's an odd thing. It's hard to think about how to measure that. But if it's not accelerating, what do you know? Well, you know that the force of the weight pulling down on it must be exactly equal to the force being pushed up on it, the normal force acting on it. These forces then must be in balance. So, if you look at one of the problems, about the problem number 1 on the bottom. A 27 kilogram mass is moving at constant velocity with 14 newtons of force being applied to it. What is the coefficient of friction between the two surfaces? Well, Let's understand the coefficient of friction has to do with two surfaces in frictional contact. All right? Two different surfaces in frictional contact. We experimentally determine what the coefficient of friction is. That's going to be then that coefficient of friction anytime those two surfaces are in contact. So that mu will be in force when two surfaces are in contact, and you can figure out the force of friction and the normal force based on that. So let's look at some givens here. The mass equals 27 kilograms. What's the weight? How do we get the weight from the mass? Well, we use the formula W equals mg. So we're just going to take the weight, 27 kilograms, 27 times 9.8, 264.6. 264.6 newtons. Now, we'll round when we get to the end of it, but we won't round internal to the problem. Okay? And the force applied is 14 newtons. Well, I have the weight and I have the force applied. Notice I don't have the normal force and I don't have the force of friction. So how do I get those? If I draw a little free body diagram, I could show that force applied, 14 newtons. Force of friction equals 14 newtons. So I could put force of friction equals 14 newtons down here. I could put my weight, which is 264.6 newtons, and obviously that should be a much longer arrow, and my normal force must be 264.6 newtons. So see, this problem is always an odd one because you're given things that you don't need particularly in the formula. It's in a free body diagram that you can see those things generate the variables you do need. The applied force, if it's constant velocity and it's in a horizontal situation, equals the force of friction, and the weight, if it's not accelerating up or down, must equal the normal force. So we need a free body diagram in order to find this stuff out, or at least prove it's the case. So now, F sub F equals mu F sub N. All right, what are we looking for? We're looking for what is the coefficient of friction. So we're solving this for this. So F sub F over F sub N equals mu. Substitution in solution, mu equals F sub F over F sub N. You can see this is nothing to this now. 14 newtons divided by 264.6 newtons. What's the only really odd part here? What's a newton divided by a newton? I'll give you a second. A newton divided by a newton is nothing at all. So we end up with a number here, 0.053. This should bother you because you're putting down a number without any units on it. But that is the way it is. The coefficient of friction is a relationship between the frictional force and the normal force. So there are no units with that. It's a coefficient. It's a ratio. So that would be how you do that. Try the second one on your own. The next one to do, maybe we could do this together, is the first one on the back page, where Ryan is a sophomore in college, and for the second time, he's doing his laundry. He did it the first time during his 8th week of school as a freshman. At that time, he had placed 16 kilograms of laundry in his laundry bag and dragged it, constant velocity, with a force of 57 newtons. Now he's dragging the same bag with a load of 133 kilograms of clothes over the same pavement. So, how do we do this? Well, you're given the mass of the bag. From the mass of the bag, can you find the weight of the bag? Well, yes, you can. Does that mean you know the normal force acting on it? Yes, you do. All right? He dragged it with 57 newtons. That's the applied force. So you can assume the force of friction is going to be 57 newtons. So from that, you can determine the coefficient of friction between the bag and the floor he's dragging it on. And it says he's using the same bag dragged across the same floor, same coefficient, and you're given the mass of it. That'll give you your weight and thus the force normal. You have the coefficient of friction, the normal force. That will give you the frictional force immediately with that. See, you just got to think it through. All right, so let's play with that. All right, so the mass is 16 kilograms. The force applied is 57 newtons. Well, what's the weight? 16 kilograms times 9.8 meters per second squared. It's 156.8 newtons. 156.8 newtons. If we do a little sketch, can I do a little sketch here? Right? The weight is equal to the normal force. Kind of a proof there, right? So the force normal equals 156.8 newtons. The applied force, 57 newtons. That's the force applied. Force of friction, 57 newtons. All right, so force of friction is 57 newtons. You can see all of this comes right out. F sub F equals mu F sub n, F sub F over mu F sub n. Okay. All right, just some simple substitution. 57 newtons divided by 156.8 newtons. So I have a coefficient of friction here of 0. Mu equals 0.36. Again, there's no units with that. That's just the relationship. Now, we have the new situation. So we're holding on to this, changing out these numbers because it's a new situation. So now it says Ryan has, the mass is 133 kilograms. Okay? The force applied is what we're wondering how hard he has to tug that thing. The weight, 133 times 9.8 meters per second squared. It's 133 kilograms times that gives you gives you 1303.4 newtons. That's the weight of it. 1,303.4 newtons. All right, so what's the normal force? All right, equal and opposite to the weight, 1303.4 newtons. The frictional force and the applied force, that's going to be the same. All right, and what I do have here now is my mu. The last thing I have there is my mu, which is 0.36. I have that mu because the surfaces are still the same surfaces. And mu is just a relationship between the two surfaces. Okay, so now, next equation, F sub F equals mu F sub n, don't even need to mess with it. F sub f equals mu F sub n equals 0.36 times 1303.4 newtons. He needs to tug that with 469 newtons of force. He's going to have to pull that pretty hard. These are the ideas of it. The key idea being the free body diagram to show you how to take an applied force and turn it to a force of friction, show you how to take the weight and turn it into the normal force. So these are key understandings to be able to do any coefficient of friction problem. There's two different things going on here. This is coefficient of kinetic friction, where he's just dragging it over. Remember? He's just dragging it over the surface. What about static friction? We know static friction is more because the surfaces have a chance to interlock. Well, what would be a way of determining your coefficient of static friction? Well, be aware for static friction, there's going to be a certain maximum amount that the object can resist up to. So let's say the static friction, the maximum static friction I could pull that this can stay still for is 20 newtons, right? 20 newtons maximum. If I pull this way with 1 newton, is it possible that that box, because of friction, is pulling with 20 newtons of force? Does that even make sense? Would that possibly make sense? Well, if this is the world you live in, when you tug something just a little bit, it flies off in the other direction. That's not happening. So when I pull this with 1 newton of force, what is it pulling back with? I think you can see quickly. It's not pulling back with a maximum. It's only going to be pulling back with 1 newton of force. Well, what if I apply 2 newtons? Okay, it'll go with 2 newtons of force. What if I apply 19 newtons? It'll pull back with 19 newtons of force. If I hit 20 newtons, right? Now 20 newtons is the maximum. It'll pull back with 20 newtons of force. What if I do 21 newtons? Well, it can't do that. It cannot pull back with 21 newtons of force. And it'll go from your locked down friction to suddenly, whoop, just sliding along. And that will then have it accelerating. If you keep pulling 20 newtons of force, or 21 newtons of force, well, now when it's static, it could hold back with 20 newtons of force, but kinetic would certainly be less. So kinetic, maybe it's only holding back with 15 newtons of force. So if you keep pulling it that way, it will be accelerating, okay? So maximum, when we talk static friction, there's a maximum kinetic friction, but that doesn't mean it's pulling back that hard. Otherwise, think about the world you would live in. That would be bizarre. So that's pretty much what we have about mechanics number 8. Has a great poem on the beginning. I would read it. I would read it 5 or 6 times till you can incorporate it deeply into your being and feel supercharged because of it and realize you're an amazing person. Thanks so much for paying attention, and see you next time.